Hello guys, welcome to my YouTube channel. So in this video, I'm gonna show you a full application about using Fortran to solve the differential equation. So in this video, I'm gonna show you how to read the data from a data file and how to use this data file to do the numerical simulation to solve the differential equation and finally export out the simulation result. So in this example, it is a little bit complicated than than my previous video, but I still try to keep this example as easy as possible because I don't want to make it really complicated. Okay, so for this example, I still use a very simple one, which is called the first order contaminant degradation because my background is environmental engineering. So this reaction is very common, which is that x1 transforms into x2. And this k is called the reaction rate constant. And the differential equation for this sequential chemical reaction is that dx1 over dt is equal to negative k times x1. And the dx2 over dt is equal to k times x1. But the thing is that in the reality, the reaction rate constant k is never a constant. It's changed all the time. So that's the reason why this one is a bit complicated because when you do the numerical simulation, your design needs to consider to capture all the reaction constant rate. Okay, so for example, let's just say the paper I just published, which is about calculating the photolysis rate constant in surface water. And the photolysis rate constant in surface water is related to the solar radiation, river temperature, river depth, suspended solids concentration, a lot of other things. So the computation actually is very complicated. So in this example, I try to keep it as easy as possible. And the example is here. For example, you see the reaction rate constant is here, and you see the reaction rate constant is changed every day. For example, for the first day, this reaction rate constant is 0.05. Second day, it goes up to 0.06, and third day is 0.07. It changed every day. This is the reason why I say this example is a bit complicated. So, and for the numerical simulation design for this example, what I did is that I try to make sure the numerical integration time step is less than 1 day. The reason why I do this is that I want to capture all the reaction rate constant. For example, let's just say the time step dt is over is 0.5. So by doing this, it can capture all the reaction rate constant. But if I set the dt, the time step is 1.5. So for the first time step, it can capture the reaction rate constant for the first day. But for the second time step, it's gonna go to the day 3, which is 0.07. So for the reaction rate constant of second day, which is 0.06, it's gonna miss. So it may cause your numerical simulation is not very, accurate and very right. So that's the reason how I do this. Okay. So as for the codes, nothing really changed compared to my previous video, but the only thing changed is that in this file, in this main file, I did something is that, for example, here, I defined the array to read the reaction rate constant data, which is here. And how to do this, I have another video to walk you through how to read the data, so you can check that video. And here is how to access the data file. I also have a video about this. And at the final, the only thing, the other thing which is new here is that I create an empty file and I want to write all those simulation data into this file. Probably this is kind of thing people feel Fortran is kind of outdated because it's not like Python. If you have Python, you can export the result and plot the result at the same time. But Fortran probably you cannot do this because it's a very old school programming language. So define the initial constant. Define the initial conditions. Everything's the same. And here is that I read the reaction rate constant data here. Use this method. And the only thing, the loop is here. For the loop, basically the structure is the same as the example I showed in my previous video, but the only thing different here is that I designed this if and else codes to make sure the integration time step is smaller than the reaction rate constant data time interval, which is a dt is less than 1 day. Because as I said, I want to make sure that this code can capture all the reaction rate constant. Okay, so basically this is the main file, and for the numerical simulation part, nothing really changed. For the differential equation part, I always use a separate file to define the differential equation, and I believe this is this is very concise and make your code easy to follow. The only thing is that because this is the reaction rate constant, I read reaction rate constant here, and I pass the reaction rate constant from the main file to the RK4 file and all the way to here to make sure the code can read the right reaction rate time step. Sorry, to make sure the codes can read the correct reaction rate constant at very time step for the numerical simulation integration. Okay, so nothing really changed, and yeah, this basically is like a summary or the combination of all the Fortran codes together. Yeah, I just don't want to make it really complicated because when you do the real model development, it could be super big and super complicated. But just really hope this one can give you some insight about how to do this. And I have run the data already, this code already, and everything is right. And I will post this on my GitHub page. Thanks for watching, and have a nice day.